Determinants. So we're given a matrix A. Like always, we generally try to make it A for a basic matrix. We have Aij, capital A this time, not lowercase. Lowercase a would mean like an entry. Aij capital means a matrix A with row I and column J erased. So you have a row and column erased. And I do this in red here. So we have this column and row erased. We have for second row and first column erased. I put red lines through it. And you just count -1, 2, -4, 1. And with determinants, this is important. So a square matrix has a n times n, we can say. Matrix, so n rows, n columns, has determinant A equal numerical value. So if n equals 1, the determinant is literally just only entry in it. Determinant A equals A11. The matrix would be A11, so determinant is A11. If n equals 2, the matrix is given like this in general: A11, A12, A21, A22. The determinant of A is equal to A11, A22 minus A12 times A21. You basically do a crisscross. So A11 times A22, and then you subtract A21 times A12. Finally, whenever you have anything bigger, which you're going to have, oops, give me a sec. If you have n greater than or equal to 3, you have a format like this: A equals so on. It goes to n, and and it's I1, I2. I is a row. If A11, A12, and then down below, well, AI1, AI2, and then eventually AN. Now the I is just is a random row, like usual. Like that's generally how it's done. So in this case, the determinant of A equals -1 raised to I plus 1, so whatever row you're in, times AI1 times determinant AI1, plus, and then you add -1 I plus 2, so on, That means the same row, basically. It's all going to be you basically can take it to the same row. That's how you do it. So I is just your row. And that's why it's AI1, then AI2. Eventually you get to I plus n. That's the end of it. The end of the row is n. This makes sense when you actually do an example or two. But yeah, A is invertible if and only if determinant of A does not equal 0. That's another thing that's an important trait. You should, just to keep in mind occasionally, just thinking. More important in linear algebra, though. Yeah, determinant Aij equals Ij is the minor of A. Yeah, it's called a minor if you take the big term Aij, like when you erase a row and column. That's a minor of A. And -1 raised to the I plus j times determinant Aij is a cofactor of A, equals Ij. So using Gauss' method, elementary operations used to get up a triangle form. This is another method of solving a determinant. You basically do elementary operations and you get the triangular form here. And determinant U equals U1 times U2 times U22. It's 1, 1, 2, 2. It's basically the diagonal. You multiply all the diagonal components and you get the determinant. And unlike before, you actually have to worry a little. So you swap two rows, row I and row j or whatever. And this causes the determinant to be negative. So originally you have A and then you have B. Well, this determinant of B is going to be the negative determinant A. So to get A, you'd basically just, whatever the determinant of B is, you just take the negative of it. Very important to remember if you ever do that. And then you can do row I equals row I plus a constant times row j. So another row, basically. You do a row plus a constant times another row, and that does not change the determinant at all. That's much more important for linear algebra at all times. Yeah, very quick. Verify that determinant equals 0. This determinant is equal to 0 by using expansions by row 2 and row 3 cofactors. So cofactors are again part of this formula. It just means when you're doing it, you take it by row 2 and do it by row 3 as well. You do it both 2 different ways. You can also do it by columns, but rows works usually very well enough. Anyway, row 2 cofactors, we have determinant A equals -1 to the 2 plus 1. So it's always negative. Then it's multiplied by 4, which is the first entry in this row, times determinant A21. So row 2 and then column 1. So it's like this. This is going to be A21 is determinant 2, 3, 8, 9, basically, because it's 2, 3, 8, 9. We got rid of the second row here and the first column. Same thing with this. So it's going to be A22 is going to be like a plus sign. You have 1, 3, 7, 8. See, 1, 3, 7, 8. 7, 9. And A23 is going to be 1, 2, 7, 8. Because you get rid of second row, third column. That's what A23, A22, and A21 is. And it's 5 and 6, of course. And just keep on going. But yeah, it's it's I plus 1, I plus 2, and I plus n, whatever nth row it is. So 2 plus 1, 2 plus 2, 2 plus 3 was it's -1 raised to that power. Eventually, you take this determinant is like simple enough. A 3 by 3 determinant, you'll immediately go to a 2 by 2, so you don't have to do anything else. You just can take that determinant straight away, because you do multiply across and subtract, like this. It's very simple. If you had like a 4 by 4, you'd basically do it. You'd have to either you do row operations to eliminate, or but yeah, basically you'd keep on going down and down. You do multiple steps. You do the same step over and over till you get back to a 2 by 2. Regardless, determinants aren't easy to take, basically, is the point. But yeah, you keep on going down, and you eventually simplify down to 60 minus 60, and you get 0. So determinant A equals 0. We do this by row 3 cofactors. We have 7, 8, 9 as our row 3. Again, -1 raised to 3 plus 1, -1 raised to 3 plus 2, and -1 raised to 3 plus 3. That's the big difference. That's one big difference. And we have our 7, 8, 9 numbers, and we also have determinant A31, A32, A33. A31 is row 3, column 1, gotten rid of. So 2, 3, 5, 6, right here. We have A32, so that's the determinant of 1, 3, 4, 6. So 1, 3, 4, 6, because you get rid of third row and second column. Then you get rid of third row, third column, so you get 1, 2, 4, 5. And you just do basic math and operations and all that, and eventually get 48 minus 48 equals 0. So determinant equals 0 yet again. Now that's all it was asking you to verify. Here's a quick proof, a sort of proof, a pseudo proof. A matrix is said to be upper triangular if for I greater than j, aij equals 0. Show that the determinant of any upper triangular 3 by 3 matrix is equal to the product of the matrix diagonal elements. So we have this matrix here, and we prove A11 times A22 times A33 equals determinant of A. So we do this the classical method. Determinant A, we'll do the upper row just to show. Oh no, we'll do the lower row. I'm going to keep it as A33. A31 is, and we'll substitute in just to show the format. We eventually can substitute in A31 as 0, and I'll make all this 0 because you take the determinant. You'll make this 0. Yeah, A31 and A32 are all 0. So that becomes 0 and that becomes 0, so all it is this second part. So it's -1 to the 3 plus 3 power, so that's just 1, times A33, so A33 stays, and it's times the determinant of A33, so that's third row and third column eliminated, so it's A11, A22, and 0, A12. Right here. And determine that's A11 times A22 minus 0. Because 0 times A12 is just 0. So it becomes A11 times A22 and A times A33. So that's the proof. And that's it. And that's it for the linear algebra review of this course.